right. So X is the real line with double origin. It's this one. And we will construct its universal cover. And we will see that the fundamental group of this is isomorphic to the group of integers, cyclic group of integers. And X tilde is defined to be this way. Let me just write down the construction. It is R cross Z divided by the following equivalence relation. So X comma N, so a real number and an integer, is related to X comma N plus 1 if and only if X is positive and N is even, or X is negative and N is odd. Okay, it will be more apparent what we are doing when I draw the pictures. Sorry? Yeah. X tilde is this. Well, actually, when I draw the picture, it will be kind. So here is what happens. So these are just real lines. And then we have the origin. And let's say this is the one corresponding to the integer 2, 3, 2, 1, 0, minus 1, minus 2, let's say. So this is X cross, sorry, R cross N, R cross Z, I am sorry. And then what we do for, what was the equivalence relation? If X is positive, then we identify even integer and its successor. When X is negative, we identify an integer, odd integer, and its successor. So for positive real values, we identify these two. So let me just, shade this region, meaning that we identify a point here with this point. For the negative ones, we identify this part, and then this part, and then we identify this part and this part. Okay. So it's like a stairs, okay, infinite stairs going in both plus and minus infinity. Okay, so you just identify this end, this end. So it's like, something like this, maybe, something like this. Okay. Now, one, of course, should check that this is simply connected, this X tilde is simply connected. How can you do this? You fix a base point, let's say X0 tilde to be this point, and then you take a path loop based at this point, and then you show that that loop can be contracted to this. I mean, it is clear that it will be like that. because if you choose a loop base at this point, its image will be a compact subset, and therefore it will just touch finitely many of these real lines. And then if it has a piece, you know, it will have pieces infinitely many real lines. You can just, for example, if it has a piece over here, you can just slide that part over here, and then when you pass to this point, it will just you know fall here, that piece, and then you swap it to this point, and then here, and then you will come here, and you can just homotop the whole loop to this real line, and then you know, this real line is of course contractible. So you can homotop the loop to a constant path. I have a detailed argument in my notes, not in this notes, but in you know, Math 537 notes. You know, all the details over there. And then what is the covering projection? So the map P is this. So P of the equivalence class of Xn is just X, okay? And we have deck transformation group. So deck transformation group is the infinite cyclic group sigma generated by sigma, and sigma maps Xn to X and X to n plus X comma n plus 2. So that's the deck transformation group. In other words, if you have a point here, you just map this to this point, okay? If you have a point here, so this point is mapped to this one, and the same thing here, you know, this point is mapped to this point, okay? You just go 2 units up. 1 unit doesn't make any difference because, you know, these points are identified, so you have to go 2 units up. Okay, that's the covering transformation. Yes. And this group is isomorphic to Z, and since X tilde is simply connected, this implies that pi 1 X is just isomorphic to the deck transformation group, since it is the universal cover, and this is isomorphic to Z. Actually, since, you know, the fundamental group is Z, there must be also finite covers, cyclic covers. Let me also describe some of them. Yes, to those subgroups. Uh, 97. Okay, so for example, twofold cover. Twofold cover. So for any integer, there is an n-fold cover. Twofold cover is this. Let me draw this using some color chokes. Okay. Suppose that x tilde is this. Sorry, x is this. And then I have this, and here a white dot and a green dot. Cover is like this. I have okay, this, sorry, yes, and then two green dots and two white dots. Okay, here, and this is my covering projection P. Here, what is the topology? So this is the double covering. You know, this has two preimages. Every point has two preimages. This yellow dot, green dot has two preimages, and so on. And I have to describe, you know, the topology. What are the neighborhoods of every point, right? Each point. The neighborhood of this point is this point plus two intervals like this. The neighborhood of this point is this point plus two intervals in the neighboring line segment. So it is a line segment like this and line segment like this. And then the topology around this point is again this point plus two intervals like this. And the neighborhood of this is just this point plus two intervals in the neighboring line segment. So this line segment and this line segment, okay? So this is the topology. So this is a two-fold cover. Similarly, you can build three-fold cover, n-fold cover, and so on, right? For the, let's say, three-fold cover, you would have something like this. And then, okay. And if we have a dot like this here, and another dot like this, and then you will have and then I have these points here. Here, what is the deck transformation group? Deck transformation group is, so here it is Z2, and it is generated by, say, sigma. Sigma is just 180-degree rotation, pi radian rotation. And here the deck transformation group is isomorphic to Z3, and it is generated, let's say, by tau, and this is just 2 pi over 3 radian rotation. Okay. And you see that you can just repeat this for any integer. Okay. So that's the covering spaces. Bunlar pek kitaplarda yoktu. Hani nedense hani real line with double origin'in şeyi universal cover'ıdır. Universal cover'ın description'ını bir yerlerde gördüm ama o finite fold cover'ları falan hani bir yerde pek görmedim. Kimse ilgilenmemiş. Yani herhalde böyle patolojik bir örnek diye görüldüğü için. Peki, şimdi şeye geçelim. Differential equations, Galois theory, and covering spaces. So, what are we going to do? We will consider this kind of equations. For example, this is one example. X is a real number, and Y will be the solution, or an equation. I can write it this way: x plus 1 over x squared, y prime. Of course, then I have to just consider non-zero real numbers. Here, x equals 0 is a regular singular point. Regular singular point. I will make precise what this means and so on for the equation. Okay. Now, if you make this variable change, x equals e to the power t, then this becomes, just a function of t. And of course, in this case, x is never 0. And actually, if we pass to complex numbers, or let z equals e to the power t, complex variable change, then we have this equation. So I can just consider the same equation, not just over real numbers, but complex numbers. And consider this covering. D is just the complex numbers with norm between 0 and 1. So unit disk, but the 0 is excluded, and d tilde is the following. D tilde is this. Nasıl? Tabii değişecek. Ha, evet. Ya bu sadece şimdilik bu örnek. Yok. Tamam. D tilde'yi de şu alırsak, complex numbers, öyle ki real part of z, let's say x, is negative. So it is this gadget. And then here we have this map P, which is just mapped to the punctured unit disk, okay? here I just take Z like this. This map, so PZ is e to the power Z, is universal cover. Why is that? Because this is a covering map, and D tilde is clearly contractible. It is just half plane, and this is the fundamental group here is so pi1 of D is isomorphic to Z. Therefore, this is an infinite fold covering. And actually, if you just choose any point here, its preimage will be just, like this, right? What are the preimages of those points? You see, P Z plus 2 pi I, right, is just e to the power Z times e to the power 2 pi I, and this is just 1, therefore this is just e to the power Z. So this is just PZ. So these points are just 2 pi unit apart from each other in the y coordinate. So the imaginary parts are just, so this is just Z. Let's say, okay, this point is, let's say, Z. This is just Z times Z plus 2 pi, yes, 2 pi I. This is Z minus 2 pi I, and so on, okay? So we see that covering space just shows up when we study differential equations. Okay. Now, what we will do, we will, carry this differential equation to this universal cover. And since the universal cover is simply connected, we can solve the equation over there. And that's the theorem that will help us let D be a simply connected region, and P and Q be analytic functions on D. Then for any Z0 in D and complex numbers alpha and beta, the initial value problem, which initial value problem? This one, d squared w dz squared plus pz dw over dz plus qz w equals 0 as a unique solution with the initial conditions, of course. W z0 is equal to alpha and w prime z0 is beta as a unique solution. So this is the typical existence uniqueness theorem that you have seen in differential equations course. There, of course, maybe complex numbers are not, included, but actually, the usual initial, existence uniqueness theorem, the proof just works in this case also. And here, the coefficient functions are given to be analytic, but you don't need actually analyticity. If they are even continuous, then there's a solution. So we will assume this result from the theory of differential equations. Here, of course, when we say simply connected in differential equation, course, we usually say the following. So it's a region, this D is a region, and it has no holes in it, right? Usually we take a rectangular region and so on. But actually, topologically, it means, just the fundamental group is trivial. Peki. Bu teoremin ispatından yani belki bahsedilebilir ama hani temelde şeye dönüşüyor. Bunu bir sistem olarak yazıp, birinci dereceden sistem olarak yazıp, ondan sonra da o birinci dereceden sistemi de aslında bir integral equation gibi çözüp şey yapabilirsiniz. Onlara girmeyeyim. Çok fazla. Yani Picard, iterate vesaire. Şimdi bu teoremi kullanacağız. Ama öncesinde covering space'lerle bu covering space'ler üzerindeki fonksiyon işte halkalarının, gerekirse cisimlerinin alakalarından bahsedelim. So, continuous functions on covering spaces. Okay. So let's take a region in the complex plane, any region. We will denote C0 with C0D, the ring of continuous functions on D. Okay, continuous functions. It's a ring we can talk about addition, multiplication, and even ratio of functions. But there you have to be careful. You know, a function shouldn't have any zero if it is in the denominator. Okay, now let's consider a covering space like this. Be a covering space. And C0 X and C0 Y denote the ring of continuous functions on X and Y respectively. Then we have a natural map. Then we have a natural map. Şöyle. P tilde map'i olacak. P star diye göstereceğiz. Map şu. P start from C0Y into C0X. And how it is defined? When you take a function on Y, you just compose this function with P and you obtain a function on X, right? So here I have X and I have P, Y, and we have a function F to, let's say, complex numbers or real numbers. Whenever I am given a function from Y to X, I can just compose it with P and obtain a function on X. So this is, so P star F is just F composition P, okay? This is a ring homomorphism. So P star is a ring homomorphism. Namely, P star of F plus G is just F plus G composition with P, and of course this is just F composition P plus G composition P. So this is just P star F plus P star G, and similarly P star F times G is just P star F and P star G. Okay, so this is a ring homomorphism. This is a ring homomorphism. Moreover, so P star is injective. And the reason is that the covering map is surjective. Şöyle diyeyim. Bir tane fonksiyon alalım. Let f be a continuous function on y. Assume that p star f is the zero function in on x. So this means what? F composition p from x to c is the zero function, But since p is onto, right, for any x in x, there is, pardon, yok ters, yok tamam. Evet. For any y in y, I'm sorry. For any y, there is some x in x, so that p of bir dakika, for any y in y, px equals y. Buradan da ne çıkar? 0 f composition p x. So this is f of px. This is f of y. But y is an arbitrary point on y. Therefore, f of y is equal to 0 for all the points in y, right? So this is true for all the points in y. And this implies that the function f is just 0. Okay? As a function on y. Therefore, p star is injective. Yani bu ne demek? So this map p star just maps C0 y into C0 x, and thus is injective, and thus by identifying C0y with its image, I may regard C0y as a subring of C0x. Efendim? Ha? Quotient. Quotient'ı değil de şey var orada. Şöyle diyeyim. With this image, but we may regard C0y as a subring of C0x. Aslında şu var, tabii elimizde şimdi x, y, şurada bir F varsa ben ne görüyorum? Şurada aldığım herhangi bir nokta aldığım zaman bunun burada inverse'ü var. Inverse imajı var. Bu burada bir subset. Right? For any point y here, I have this subset here. And all those subsets are mapped to the single point. So this is F composition P. So all these points are just mapped to the point F of Y. So I can just describe this subring as what? So C0Y can be identified with the set of functions on X so that G is constant. G is constant. Of course, you know, G is an element of C0X, and G is constant. G is constant. Constant on each fiber P inverse of Y. Yani bu halkayı şey diye görebilirim. Halkayı I can regard this subring as the elements of C0X so that it is constant on each fiber of the projection map P. Okay. Well, if I have a special covering, if you know this is a regular covering, then we have a better picture actually. Şöyle yazayım. In case where P X to Y is a regular or normal covering.
Hocam tahta değişmedi galiba.
Pardon. Normal covering. Then we have a stronger result. Namely this one. Yazalım. Assume that P X to Y be a normal or regular. Buna normal da diyeceğiz. Aynı zamanda buna böyle cover'lara Galois cover da diyeceğiz. Covering, Galois covering with deck transformation group. Let's say gamma, let me use Book's notation, X to Y. Okay. Then so P star of Cy, which is a subring of Cx. This is a subring of C 0x is isomorphic. Aslında isomorphic değil. Is the subring of C0x that are gamma invariant functions on X. Yani şu P star C0 Y is equal to C0X. Here I write gamma. What I mean by invariant, I mean the following. These are functions so that for any element of this group, well, let's say gamma, so G composition gamma is equal to gamma for all gamma in gamma. Resim çizeyim bir tane. Yani şimdi elimizde x var, x var. Bir tane gamma ile burada şey göstereceğim. Covering transformation'ı. Yani bu ne demek? P equals P composition gamma. Gamma is any element of the deck transformation group. So if I have any point here, any function here, burada tabii garip bir şey yazmışım. Burada f aldık. F, şurası f olacak. Veya ikisi de g olacak yani. Bakayım ne yapmışım. Evet. G alayım şöyle. G, G map'i şu. Bu G map'i gamma'nın etkisinden bağımsız. O da neden? Çünkü şurada bir y noktası aldığım zaman bunun üzerinde işte şurası P inverse of y. Şurada herhangi bir x aldığımda şu nokta işte gamma x. Fiber'da bir başka nokta değil mi? Deck transformation'da. Ben ne biliyorum? Buradaki bir fonksiyon işte f'i diyelim ki f bunu f of y noktasına götürüyor. Bunun lifti olan fonksiyon g bütün bu fiber'ı tek bir noktaya götürüyor. Dolayısıyla g'nin x'te aldığı değerle gamma x'te aldığı değer aynı. Örnek vermek gerekirse example, for example, consider the covering transformation from R to S1 given by işte e to the power 2 pi I t. So yes. Okay, yeah, okay. zaman bitireyim ben şeyi. Şunu